Let's continue with the test review. So we finished chapter 21. We discussed all the equations. We did not discuss this one. So we discussed it in class, but we didn't really use it, so don't worry about this one. Let's go on to chapter 22. So the first thing here is the flux. So the flux depends on the strength of the magnetic field, the area of the loop, and the relative directions. So basically, if you have magnetic flux through a surface, through a loop, really it just means that you've got those magnetic field lines that are cutting through that loop, and then you have flux, right? If the magnetic field lines are not cutting through that loop, they're parallel, you have no flux. So the angle in this equation here is not the angle between B and A, it's the angle between B and the normal to the loop. So the normal to the loop, let's say, is up. You can think of it as mu if you had that current loop, but even if there's no current, it's normal to the loop. So the normal is parallel to B, the angle is 0, and that gives us the maximum flux because we've got a lot of magnetic field lines going through that loop. So that's what you want to visualize for this first bullet, and this is what you want to visualize with the second bullet. The normal is going this way, it's perpendicular to the field, so the angle is 90. When you plug in 90, cosine of 90 is 0, you get no flux. So what we want to be able to do is figure out if the flux through a loop is changing. So if you've got a loop of wire and the field through it is getting stronger, or the area of the loop is getting bigger, or the field is changing directions as it's rotating through the loop, then you know that one of these variables, BA or theta, is changing. You know that the flux is changing. And then Faraday's law applies. So Faraday's law gives us how much EMF is induced in this loop. So it depends on how fast the flux is changing and also the number of loops. But really, the faster the flux changes, the more EMF will be induced in that loop. And remember, EMF is a voltage. So you need to be able to calculate this. So we've had multiple examples. So let's say it tells you that the field is changing inside the loop. Then Faraday's law would become E equals negative N. And then you're not changing the A for the flux, so you take that out of the flux. You're not changing the angle, and let's say that the field is perpendicular to that plane of the loop, so you've got the max flux. When you have the max flux, you don't even care about the angle. Then you just care about, well, how fast is that field changing? And then you just plug in your numbers, and it will tell us how much EMF is induced in that loop. Don't really worry about the negative sign, because Lenz's law will tell us which way is that induced EMF and current. But Faraday's law just tells us how strong is the EMF, and then you can always do the current is that EMF divided by the resistance, if it's a simple circuit with a resistance, to find the current. So examples that you want to be familiar with, in addition, we've talked about several examples in class, especially these two. You definitely want to go and look at all the examples, but these are just two examples. So it doesn't mean that that's the only thing you're going to see on the test, but I just want to go over what these are. So the motional EMF is whenever you see this bar that is moving and is connected to this external circuit, and there's a resistor here, and there's some kind of magnetic field here. It can be into the page or out of the page. I'm drawing the magnetic field into the page here. And then the bar is either moving to the left or to the right. So when you have this kind of situation, it's called motional EMF, and what we care about is this loop here. Right? A loop doesn't have to be circular, it can be rectangular. And the flux through that loop is changing because the area of the loop is decreasing in this case. So we don't have to use Faraday's law and see how fast is the area changing. We can go straight to using this equation right here for motional EMF. Plug in the external field, length of the bar. This is the bar here that you are given the length of this bar. And V was the speed at which that bar is moving. And then another equation, another instance, right there. I'm remembering now the reason I mentioned these ones is because there's special cases of Faraday's law where you don't have to use this equation, you can use one of these equations. So if it's a generator, and the way to visualize that is that you have some kind of loop that is rotating, and there's some external field, let's say it's out of the page. So you can see that when the loop here is in the plane of this paper, you've got lots of flux, you've got lots of field lines going into that loop. But as this loop is rotating, sometimes the loop is going to be perpendicular to this plane, and it's not going to catch any field lines. There's not going to be any flux. So this is another way that the field can change through the loop, changing the flux, and we can go straight to using this equation to give us the maximum EMF induced in this loop. If it's asking for the maximum, then you just cross out the sign. And you just need to know how fast is that loop rotating. And omega is the angular frequency, which is related to the regular linear frequency as 2 pi f. And omega is in radians per second. So you need to know the area of the loop, the external field, the number of loops, and you can find how much EMF is induced. You don't have to use Faraday's law.